Thank you. This is the final ITC lunch for the academic year, and I think it's going to be a lot of fun. I'd like to introduce, for those of you who don't know already, Xiao Alves, who's going to be the podium speaker later this afternoon at 4. Xiao is a Radiative fellow, so we'll get to know him plenty of time to get to know him. I'd like to have us all thank Anastasia Outflow for organizing so much of this. Eric Keto is over there. Among his, in addition to his support of the Keto Prize, he's generously continuing to support the ITC Lunch. And Or Brower will make a brief announcement.
Hi everyone. So I'm all Anna Grau, at least for today. For the last year, 10 high school students have been working with some of us here on independent research projects through a program called the Science Research Mentoring Program, which I direct. This program is ending at the end of May this year. There will be Thank you, I forgot about that. There'll be an end-of-year symposium for this program on Friday, May 25 in Pratt between 4 and 6 o'clock. The students will present the results in talks and a poster session. You're all invited, and not only that, I'm asking you to come to show these students that they are being taken seriously and professionally. I also think that you'll be very pleasantly surprised by the results. The program will continue next year, so I'm looking for mentors now. If you're postdocs or advanced graduate students and you want to work with high school students, please get in touch with me. Thank you.
Thank you. So now to the main program, and our speakers are Anna Bonaca on the Gaia DR2 view of the GD1 stellar stream. Then we'll move on to Anna Rosen on the formation of massive stars with radiative and outflow feedback. Then we'll hear from Anna Barnacka, the art of turning galaxies into telescopes. And we'll close with Anna Pancoast on the stability of broad-line region geometry and dynamics in Art 151. And if you haven't noticed the conspiracy there, you. Go ahead.
Thank you, Charles. I'm really happy to be able to share some of the Gaia excitement I've had for the past 7 days with all of you. So I will be talking about a stellar stream discovered in the Milky Way halo called GD1. And the interest will be mostly coming from a cosmological context. So we know that simulations of cosmological simulations of large-scale structure also predict that there is a lot of structure on small scales. And so here I'm showing a visualization of a cluster simulated by Sonak Bose over here, who started with like 10 to the 15 solar mass halo and is working his way down the mass function over 10 orders of magnitude. So there are these smaller clumps of dark matter predicted to exist, but we haven't yet been able to see them as they do not retain baryons in them. And so, but as any good theory, lambda CDM does predict that this should have an effect on other bodies that are present in galaxies. And so what I'll be most interested in is what effect they have on tidal streams from globular clusters. And so just to kind of get some intuition of what we expect to see of globular clusters evolving in a smooth and static halo field, here is some random sampling of globular clusters being disrupted on different orbits. And so you see stars leaving the main body of the cluster and being extended in the in space, in galaxy. And so there are many different morphologies you can see, but they look fairly irregular. Whereas when you move into a cosmological halo, such as that from Via Lactea simulation, and look at similar streams or streams on similar orbits, you start seeing differences between those. So, for example, like this has clear change in shape with respect to its analog in the smooth halo. And in general, the streams are more disturbed, have gaps or even stars dispersed from the main body of the stream. And so this has stopped being an academic exercise, basically with the arrival of the SLON Digital Sky Survey. So having this awesome big data photometric data set enable people to make these maps of the stellar halo, such as the one I'm showing here, where in different colors I'm showing melapore stars in the halo at different distances. And so a lot of structure is apparent here, the biggest of which is the Sagittarius stream over here spreading. Then you have many compact objects such as globular clusters and dwarf galaxies. But then here when we look into this corner, the globular cluster Palomar 5, we see that it has two tidal tails extending from its main body, and then this is the kind of object that I'm interested in studying. And the particular object that we'll be talking about today is the GD1 stream, which is starting here and then arcing all the way up there. So this is the longest cold stream, or the longest remnant of a globular cluster we've discovered in the Milky Way halo. And as such, we thought it would be a most promising object to tell us something more about the galaxy itself. However, it's a challenging problem, right? Milky Way is a 10 to the 12 mass galaxy. It has many stars, whereas a globular cluster has maybe 6 orders of magnitude fewer. And so I'm showing here a map of GD1 stream from SDSS data. And so it's in this GD1 coordinates such as almost aligned with 5, 2 of 0. And you can see it as an overdensity, clearly, like the black line. However, it is very noisy, and this is created by binning and weighting each stars in each bin by their position in the color magnitude diagram, basically. And if you wanted to say anything about the small-scale structure of the stream, it would be extremely hard, because you can see that in this background regions where you expect only the Milky Way stars, that you get similar order of variations. And so it's been, people tried counting gaps or finding gaps in this shallower data from surveys such as SDSS, but they haven't really been conclusive because of the issue presented in this figure. However, we have good news. Last Wednesday at 6 a.m., Gaia data release 2 happened. There was a lot of excitement. Some of us were also awake at the time, and among those, in the first 2 minutes, trying to download data from the archive. And people were so excited about this data set, because for the first time, now we have not only positions and colors of stars in the Milky Way, but also some measure of their motions. And so I will just briefly show this movie from the Gaia team that shows at first stars in Gaia colors, and then it will forward them 800,000 years into the future. So you can kind of see the moving groups coming over, and then some very high velocity stars. And this is for a subset of 96 million stars that are very nearby to us, so that in this Gaia data release, they have full 6D phase space information. Where GD1 stream is out in the halo at 8 kiloparsecs. So unfortunately, those stars were too faint to have radial velocities released from Gaia, but they do have exquisite proper-motions. I'm now going to show what we can do even with just this data. And so, so with Adrian Price-Whelan, I queried the Gaia archive in the region where we expect GD1 to be and selected only for distant stars. So we just made a cut of stars having parallaxes less than 1 and show their positions here, and you don't really see anything because there are still like many stars in the Milky Way that are farther away than 1 kiloparsec in that region of the sky. However, when you plot the proper motion diagram, you see almost 3 distinct features over here. So one is centered on 0. Those are the halo stars. Then we have the disk rotating at positive proper motions. And then this smaller feature over here that appears to be moving kind of along this axis of the that's aligned with the stream. So when we select, just make the additional proper motion cut, selecting the stars in this box, we get image of a GD1. And note that this is not binned. I'm just showing positions of stars only selected on proper motions from Gaia. But then being here at Harvard was really great because people have curated many photometric catalogs. So I don't see Catherine here, but Catherine Zucker did a great job loading all of possible photometric catalogs into our computer systems. So within a day, basically, we were able to not only make a selection in proper motion space, but also in color magnitude space. And so here's the color magnitude diagram of stars in that box in proper motion. And so you can clearly see like this structure. Okay, maybe you can see, but RGB is here. But what we definitely see is the subgiants and then the main sequence stars. And so when we further select only stars in this region of the color magnitude diagram, we get the very clean, or the cleanest look at the GD1 stream that we've had so far. And I will just go over some, at this moment, fairly qualitative aspects of this map. So the first thing to note is that we definitely see the difference in width of the stream. So it's kind of thinnest here and becomes very fluffy at the negative pi1. And basically that part was completely invisible to previous studies. I'll be done. So we think that this may be the location of the progenitor at the thinnest and densest part of the stream. And then there are the two very obvious gaps and something that appears to be GD1 or overdensities of GD1 stars removed from the main body of the stream. So we have like this blobby feature here and something that looks like a spur over here. Just a comparison what the smooth model would look like, as people have shown that you do expect density variations just in those kinds of models. So showing the data on top, the model in the middle, and then the density profile of the data in blue and the model in orange. And so we match the highest and the lowest density, but they're like the density variations in the data are much larger than those in the model, and they're not associated with dust. It's a very high latitude field, and it's also not associated with the Gaia scanning law. So there remains a lot to be done, both in terms of modeling, as we think one likely explanation for for the existence of both gaps and the extra material beyond the main track of the stream is following an encounter, maybe with dark matter subhalos. And if that's the case, then it will be very informative to have radial velocity on all of those stars, because then we'll be able to calculate energies and then have a much better handle on what the initial perturber was for the stream. And I will take questions now.
In both Palomar 5 and the new toy model, it's a little break at the beginning. It doesn't seem to show up on the screen here. Can you comment on that?
Right. So, okay, this is a tentative progenitor, so there's a question for a reason. But we do think that this is kind of a very last stage of disruption. So I'm not sure that our models are how reliable they are in this regime where there's, where you're actually going to no mass in the progenitor. So I would, not put too much.
Could you go 2 slides back? The one before you did the discussion. So at minus 20 in slide 1 in the top panel.
Yeah.
I see the gap a little bit in Milky Way stars too, so like a white line.
Oh, that.
Is there something that may be related to some sort of instrumental thing to that particular gap?
If you mean on the same thing, this is much narrower than the gap. So it would, I think the Gaia scanning pattern doesn't have definitely that scale. So the gap is 4 degrees wide, and all of the scanning patterns are much smaller.
So if ultimately you find that there is a need for interaction with substructure, is it clear that it has to be complementary substructure and not baryon substructure?
Yeah, that's a good question, and I will just pull up a figure from the paper. So this is the orbit of that model, and so here is the RZ plane, and the vertical line, or the black line, is 99% of the stellar mass of the disk. So it appears where the stream crosses the galactic plane is far like a 13 kiloparsec, where there's really no matter. So I think any GMC interpretation would be contrived, but yeah.
We'll take one more question.
So you went velocity, photometry, and then again velocity. So if you now take the different clumps you have and go back into photometry space, I guess you have 5-band photometry. Do you see any difference between them?
I'm not understanding.
So I mean, you select them, you can. That's if you have different spurs. So if you then project them back again into photometry space, do you see any lines or any multiple populations or something like this?
Oh, there are too few stars in those spurs. So I do have like a figure where we looked into more detail on what is the population and what's the color magnitude diagram of the spur and in the off field. So you see more stars in the spur definitely, and they have similar proper motions to the stream at the same phi 1 kind of thing. But I think either with deeper data to identify more members, such as with HSC proper motions, or just getting radial velocities, I think would be really useful, because then you can match in chemistries.
Great, thank you. Okay, so today I'm going to talk about a project that I'm finishing up. Working on this with Alyssa Goodman here and my PhD advisor, Mark Krumholtz. And I'm trying to study how the combined effect of outflows and radiative feedback actually affects the formation of massive stars. And so the idea for massive star formation now is that massive stars form in a similar fashion to low mass stars. So you have a dense, massive clump of gas, cloud of gas, that then can fragment into massive prestellar cores that can then collapse into massive stellar systems. And for these types of cores, they tend to be dominated by their turbulent pressure rather than their thermal motions. And they also tend to be have virial ratios of about 1 or less than 1. And so if the virial ratio is less than 1, then they're prone to collapse and to form a massive stellar system. Last time, so I gave a ITC luncheon last fall, and I showed some work from my PhD where we studied how radiative feedback actually affects massive star formation. And one of the biggest problems in trying to understand massive star formation is the fact that while they are accreting, they can reach the main sequence and have really high luminosities, and so the radiation pressure associated with their high luminosities can actually overturn the accretion flow. And this can cause matter to be blown away, so you wouldn't expect to get stars that are above 20 solar masses or so. But it turns out, instead of looking at 1D simple spherical models, you can actually overcome this by performing 2D and 3D models where you develop an anisotropic accretion flow. And so for a while, the main idea was that the collapsing core has angular momentum, you form an accretion disk, and then you can accrete material from the accretion disk, and then radiation can just blow material away from the poles of the star. However, we did a 3D simulation and we included turbulence, and what we found is that there's multiple ways that you can actually feed the star. And the first is the fact that with the turbulence itself, you get these dense filaments that can be unimpeded by the radiation pressure, and you can deliver a significant amount of mass that way. And then as the core collapses, you form an accretion disk, and so that's another form of material to bring to the star. And then finally, you can also develop these Rayleigh-Taylor instabilities in the shell that can bring material down to the star. And so, in essence, the radiation pressure barrier is no longer a barrier. But there's other forms of feedback that needs to be considered. And for example, one thing to consider is collimated outflows. These are typically magnetically launched due to the interaction of the star with an accretion disk. And these outflows are launched along the polar directions of the star. They have high momentum deposition, so they could push material away and then sweep up mass as they expand. And then this mass can be ejected from the core itself. And so, for example, if you compare kind of like the momentum and energy deposition from radiation and outflows, you find that the energy deposition from radiation dominates greatly over outflows, but the momentum injection by outflows is much larger than that for radiation. And so you expect that for the momentum budget, outflows should be more important. And so to kind of just build up upon that, we wanted to see, well, how does the combined effects of outflows and radiation pressure affect how mass is delivered to the star? So what I'm showing here is a simulation now where we include radiation pressure from both the direct absorption of the stellar radiation field using an adaptive ray tracer, and then also the dust for process radiation field, because the luminosity is so high, or we have high UV luminosity, and so the dust is highly opaque to that, it'll absorb it, and then reprocess that, re-emit it in the infrared. And then we also included outflows, and we have a subgrid model for that, where the momentum injected, we also include thermal energy and kinetic energy injection, but like I said, momentum is very important, where the momentum injected is just the mass loss in the outflows times the velocity of the outflows, and we assume, based on observational estimates, that about 21% of the accreted mass goes into the outflows, and that the outflow velocity is about 30% of the escape velocity of the star. And so what I'm showing here is the top panels are the full core, so 40,000 AU, and the bonded panels are zoom in at 8,000 AU. And what you see is that these panels, this is along the XY plane, and this is along the YZ plane. And so we see it with turbulence, and then we form a star, and then the outflows start to eject mass early when the star is still low mass. But still, you can have the filaments that come in from the turbulence accrete into the star. But then eventually, as the star gets more and more massive, you can eject a lot of material from the core. So here I'm showing as a function of time for both runs. So I'm comparing this to the impact of both radiation outflows to a case where we just include radiation alone. This is 150 solar mass core, and as you can see, as it collapses, the outflows can eject a lot of material, whereas for the radiation case, the core just starts to collapse, and you can bring more material to the star. And because of the imposed, the fact that you lose accreted mass due to the outflows, the mass of star in the radiation-only case grows a lot faster. And so that affects the Eddington ratio. So these are these plots here. And so Eddington ratios are greater than 1. The radiative force is greater than gravity. And so you see that you become, because the star is more massive, so at the same time, you have a larger region of the gas that has higher Eddington ratios. Also, because the star grows slower and also the outflows kind of lead a path for the radiation to leak out, you see that the development of Rayleigh-Taylor instability, so you can see the instabilities along here are less prominent when you include outflows, and that's because the radiation can escape outwards. And now we can look at how mass is ejected. So these are rho VR plots, so the radial velocity with respect to the star. And this is along both panels are along the polar axis of the stars. And what you see that when you include outflows, you can eject a lot of material along the polar axis of the stars, and these lobes increase with time. But still, you get a lot of material along the accretion disk towards the star. Whereas when you have when you don't include outflows, you just develop these Rayleigh-Taylor, these radiation pressure dominated bubbles that expand and then eventually become Rayleigh-Taylor unstable. And so the momentum injection from outflows are necessary to eject material from the cores themselves. The radiation pressure is not going to be able to do that. Likewise, we develop an accretion disk because the core itself, due to the turbulent velocity distribution, we have a net angular momentum, and that accretion disk will grow with time as material with higher angular momentum falls down towards the star. We see that we develop a disk pretty early, but then you can also see that that disk eventually becomes disrupted, and that's likely due to the fact that you have accretion of low mass stars and passing through the disk and all that, but you do build up an accretion disk again. And so and because you eject a lot of the material along the poles, disks are crucial to massive star formation, especially at late times. And then if you look at the accretion history of these runs to compare, you find that, of course, when you don't include outflows, the star grows a lot faster. And just looking at the difference between these two runs, you find that the stellar mass, when you include outflows, is smaller by a factor of about 30%. But considering that we, choose to launch 21% of the mass in our subgrid model, that means that there's only an 8% difference. And so what that says is that at least during the early phase of star formation, so this was a little less than a free fall time, you find that outflows do not have a significant effect on reducing the accretion onto the star. Likewise, you can look at how the companions are created. So we create multiple companions in both of these runs. And in the beginning, that's dominated by turbulent fragmentation. So you can do the turbulence, you can develop regions of high density that can then collapse into companion stars. But the turbulent fragmentation will be suppressed when you have radiative heating. So for the radiation-only case, we have much less companions until we develop a significant accretion disk, and then you can actually have the disk form companion stars due to disk fragmentation. And then finally, you can also look at the properties of the cloud itself. How does the feedback affect the gas that surrounds the star? And so I'm showing both mass-weighted and density-weighted, and volume-weighted quantities. And the reason why I want to show volume-weighted quantities is because the outflows are going to launch out a lot of the low-density gas. And you find that the inclusion of outflows significantly makes the core unbound. If you look at the volume-weighted quantities, it makes the low-density material be pushed out. And you can easily see that in this volume rendering here. Furthermore, if you look at the temperature profile of the gas, because the radiation kind of is vented out through these polar directions where the gas is launched out, you're able to lower the overall temperature of the core. Okay. And then, okay, so one thing, and I'll go through this quickly because I know someone will ask about magnetic fields. So I also wanted to consider how does magnetic fields affect the formation of massive stars. So now we have radiative and outflow feedback plus magnetic fields, and we take the fact that dense molecular gas tends to be supercritical with mass to flux ratios of 2, so they will still collapse, but the collapse will be slowed down. And so this is showing the same thing. And so the structure is a little bit better. The magnetic field kind of smooths out the structure a bit, so you don't get this turbulent fragmentation. You also get lower densities than before because of the slowdown and the collapse. But you still see that the outflows can still push out some of the material. Okay, so one thing you notice is because the density is lower is that the regions, the outflows themselves are wider. The collimated part becomes wider. Also, the accretion rate is a bit less. And so, for example, at the same stellar mass, the final stellar mass is about 20% lower. And finally, you can look at the outflow properties, and you see that you would expect, with the presence of magnetic fields, that the outflows themselves should be less dense and then also appear less collimated than when you don't include magnetic fields. And then I will just leave my summary up. Thank you.
So since some of these processes might depend on metallicity and others don't, do you have a kind of qualitative sense of, one, was this done at kind of assumed solar metallicity, and the other one is, how much that will actually, the picture will change?
Yeah, so if you lower the metallicity, radiation pressure won't be as important because you won't have dust. So for example, pop 3 stars, radiation pressure is not important at all. So you could think of, like, let's say the LMC, for example, the metallicity is like half solar, so radiation pressure should be less of an impact. If the outflow properties do not depend on metallicity, which they probably don't, then you wouldn't expect a difference for that. Another thing which I'm going to be looking into next is stellar winds, and that will also depend on metallicity because the winds are radiatively launched, and so if you have less metals, you have weaker winds. So you could think that maybe it's easier to make more massive stars in lower metallicity environments like the LMC, and we do see more massive stars than we see in the Milky Way. So yeah, metallicity should definitely have an effect.
So I don't know, you might have said this, but how collimated are your lower jets in these models?
Oh, I did not measure that. So the subgrid model, we do a 0.01 degree or 0.01 rad angle. But basically, total angle. Well, yeah, like how we push it, just with the subgrid model. So it's basically kind of encompasses probably like a cell along the star, like the width of a cell. But as it sweeps up mass, then they widen out. Yeah, and I haven't measured like the actual like size. I just looked at it.
You mentioned companions, but since we now know that massive stars are very likely to have massive companions,
Mm-hmm.
what is likely the most important thing that your simulations are showing would lead to that?
Sadly, not much because well, there's two things that can happen. So we have 28-year resolution, so we can't find we can't simulate the birth of like very close in companions. So that's a problem. But one thing that we do find is that we do have a lot of dynamical interactions. So I didn't show it, but in other runs that I've done, you do see that like as the low mass stars pass by the massive star, they could come into a tighter orbit and stuff like that, or be ejected. Another thing too is what we get in the end is dependent on what assumptions we make. So one example is how we decide to merge star particles, and we're not strict on that at all. So for example, in Mark Krumholtz's 2009 paper, he gets a nice massive binary, but for him, anything that passes within 40 AU of each other merges, whereas we have a more stricter criterion for merging, and so that's why we're left with a lot more low mass companions because we can't properly model the merging.
Let's thank our speaker again.
Oh, yeah.
Is this one? Yeah. Okay. Okay. So I am Anna Barnacka, and today I will tell you about my collaboration with an artist on my project on gravitational lensing. So first, let's start with the motivation, how I started working with an artist. So I was working on a review article on my work that was describing using gravitational lensing to study the complexity of active galaxies, and using lensing to find out from where the emission is coming from active galaxies by using gravitationally induced time delays, and also combining them with the Hubble constant, or just using position of the mirage images. But I ran into the problem that all illustrations of gravitational lensing include, of course, we have a lensing galaxy that curves space-time, and we have a quasar. And those quasars are always shown in those illustrations as a point sources. And in my research, I was showing that actually quasars, especially when they are the most luminous one and radioactive, and also with a lot of radio emission, they have powerful jets. And those powerful jets have very complex structure, from radio up to very high energy gamma rays. So I needed illustration that would show also the complexity of the sources. So the idea was simple. Let's involve an artist who will illustrate this complex idea. So that was the solution. So now, so first of all, we have a galaxy that curves space-time, and curved space-time tells the light how to move. And depending on where the emission originates, the light will follow different paths. So now, when we have a galaxy, now instead of having a point source, we have a galaxy, we have also the central part, and we have also jet. So now, the emission that comes from one part of the galaxy, let's say it's close to a massive black hole, will follow those multiple paths. And also, when the light travels through those two different paths, it's traversing different gravitational potential. So I wanted also to illustrate how the time delays how they originate in this picture. So when the emission is traveling closer to the center of the lens, the clocks run differently, and the emission then the time, those paths, there is a time delay between those two images, and closer the image travels to the center of the lens, there is a larger time delay. So now you can see that we have those two paths for one emitting region, and we have those two flares that travels through the galaxy. And we have a different time delays depending on from which path across the galaxy the light travels. And then the light converges into the observer. We have our galaxy, and also we have an observer somewhere on the edge of the galaxy where we live. But many of you ask me, okay, this is the final result. But I got a lot of questions like, okay, how did I meet the artist? How we started the collaboration, and how we actually ended up with this illustration? So I will tell you the story from the beginning. So first, we met during one of the meetings at the Harvard Kennedy School with the Polish Prime Minister. So it's me annoying Polish Prime Minister about his vision for science in Poland. And in the meantime, there was also a lot of people. And there was also one artist that told me about her work on promoting girls in STEM. And it was fascinating that she was using art as a tool to involve kids and to promote an idea.
Then I needed the illustration. So I invited Marlena for collaboration, and we started working together in December. So we started first, we had to figure out first, okay, what do we want to communicate through the painting? And we needed a very complex source. We needed a galaxy, active galaxy with the jet. And also, we wanted to point out that actually you may have two different origins of the emission. And when we have two different origins of the emission, from each place, the emission will approach to the galaxy from different distances, and they will follow different paths with different gravitational potential. So we will have different time delays depending on where the emission was produced. Then, first we started illustration with an Earth, that we have Earth and we have a little telescope somewhere, and the image is produced. But then when we look at it, it looks that the Earth is next to the galaxy. So we needed to change slightly the idea and put a galaxy there. And then, of course, it was still, the galaxies were kind of, the composition wasn't perfect. And we had to go through over and over again to find the perfect composition. And also, this painting had to include as much science as possible, had to be accurate. So the magnifications here of those mirage images, they are as you would expect to see. Also, this image is like this is what you would see. So first, this extended emission, this ring, this Einstein ring, is produced from the host galaxy that is well aligned with the center of the lens. Then we have two different emitting regions, and each of them have two mirage images. And those mirage images actually are accurate, exactly as we would obtain through gravitational lensing. So we come up with the idea with that sketch that was scientifically accurate. But then we also needed something that would look also very engaging and beautiful. So Marlena painted this nice painting, but we had a massive problem. Because when you take a picture of this painting, it just looks horrible. So can I get some light? I wanted to show you the painting because it's, can you get some light? No? So anyway, I wanted to show you the difference between the original painting and the image of the painting. Because it's fascinating, because... Okay, anyway, I will...
Hold it in the light there.
But I wanted to show you, so I will just go around you. And so there is a big difference how our eyes perceive images and how camera does it. CCD cameras are linear, and our eyes are more logarithmic in scale, and also the way how we see colors is very different. So on this image, you see this dynamic with full of colors. But when you're taking the picture, it just disappears. So it's completely different. And I needed a painting that I could use in the publication. So it was also amazing to see how different camera and our eyes perceive images. So we needed to come up with something that would use colors and would look very appealing, but at the same time, we can take a picture and add it to publication. So then Marlena went back to work, and she was working a lot, sending a lot of different versions, which I didn't like. And then, finally, she sent me an email that yes, she got it, that I will love it. She used cubism and futurism to depict lensing. And yeah, it was amazing. I love it. And it was also very interesting because I knew a bit about cubism, but decided to find out more because we didn't discuss what kind of style she should use. Because already she was so constrained by all the science I wanted to keep. So at least I wanted her to at least have a freedom to use colors and styles. And she used, so naturally she used cubism. And then I started reading more about cubism and also connection to relativity. So what was for me very interesting is that Henry Pincare's work on geometry actually inspired both. So had a lot of inspiration for science and art. In science, it was an inspiration for Einstein's general relativity theory. And in art, Picasso used it to create the cubism. And when you think about cubism, in cubism, the single viewpoint was abandoned. So always painters would just use one single perspective. In cubism, the cubism uses geometric shapes, interlocking planes to represent reality. And it's very interesting. So a cubist is using geometric shapes, interlocking planes. And when we think about gravitational lensing, we have all of those planes. We have image planes, we have lens planes, and we have geometry of the space-time that is shaped by the mass. So cubism and gravitational lensing interlock each other so well. But that's not the end of the story, because then Marilena took those paintings and did like a class for girls in STEM. So those are girls scouts painting using these lensing paintings, and they having a lot of fun, and they painting galaxies. And it was for me kind of amazing to see that people can have so much fun with my research. And I decided to try it myself. About a few weeks ago, we had Cambridge Explores the Universe. And we have an exhibition here of art and science. And we had hundreds of kids coming. And they were painting black holes. Within half an hour, we ran out of black holes and had to go and print more. And those kids have so much fun. And also, when you allow kids to actually paint something, it also develops the sense of ownership. To conclude, our scientific research becomes infinitely complex. But art gives us a tool to tell our story in a way that is very engaging and beautiful. And a bit of advertisement. So thanks to Avi, we actually started a group of art and science at CFA. So if you want to join, to see that other people, make sure that other people have also fun with your research, you can just email me. And also thanks to our wonderful librarians, we will have a first drawing classes at CFA in May 21st. So please join if you are also interested, you want to have some even more fun. Thank you.
Since you mentioned that, since gravitational lensing produces time variability as well, if you looked at the possibility of using video art to and add the time.
Oh yes. So actually, we have tomorrow. We will have a next meeting, and one artist who is also in our group, he's using like a very simple drawings, animations that can be done by kids at school. So we look into that as well.
Any other questions? Oh,
Yes.
yes.
In the science education world, they talk about the difference between education, not education, engagement, and then content, and learning about the content. And so I think this is fabulous in general, but I just have a question about the engagement is clearly going to be really high, and I'm curious about the actual content that people get out of the images. How much do you know about that?
So actually, it was actually very interesting because there is a the art. The painting had like a lot of different dimensions. You can go very deeply into science and talk to scientists. And the thing they were learning is the concept of a galaxy. Because kids understand, okay, that we have planets, we have the sun, but they don't really understand, they didn't know about that we actually live in a galaxy. And in this painting, we have this tiny telescope on the edge of the galaxy that was representing our place. So those kids were so excited to learn that, oh, this is our home, we live here. So they were learning the concept of the galaxy and also what is our place.
Cool. Thank you.
Pierre?
One more. And then we have to move on.
I just have a quick question. Like, I might be wrong, but I thought most of the optical depth in strong lensing surface are elliptical from elliptical galaxies.
Actually, no. You mean as lenses? It depends depending whether you're looking for galaxy lensing or galaxy quasar. With quasars, with galaxies, people look. There is like a selection bias. People look for like very massive elliptical galaxies as lenses because they want to understand the mass distribution of the lenses. So if you have a galaxy, then yes, but it's a bias. With quasars, you are not biased by the lens. So you have like, you really see what kind of galaxies are in the universe, and at least like half of them are spiral galaxies. So it's accurate.
So let's thank Anna again.
Thank you, everyone. So if we want to understand how black holes grow and evolve, then we need some method for measuring their masses outside of the local universe. And to do this, we can use active galactic nuclei, black holes that are actively accreting, by actually substituting time resolution for spatial resolution and resolving motions of gas deep within the gravitational potential of the black hole in the broadline region. And the broadline region is so named because gas there is moving so quickly around the black hole that the emission lines from this gas are actually broadened. And this means that we have a direct handle on the velocity of this gas. So if we want to measure a black hole mass, we also need to know how far away this gas is from the black hole. And for that, we can use reverberation mapping. Now, the way reverberation mapping works is that accretion disks generate stochastically variable light that we can monitor, as you can see here. But that light also propagates out to broadline region gas, where it's reprocessed into broadline flux. And so you can see here that it has similar variability characteristics, but with a time lag, tau, that depends upon this light travel time out to the broadline region. And so you can combine this time lag with the width of the emission line profile and measure a black hole mass. But there's one final thing you have to worry about, and that is the normalization of this mass. And that encapsulates all of the detailed geometry, dynamics, and orientation of this broadline region. And unfortunately, because we can't yet spatially resolve the broadline region structure, what's usually done is to use an average value of f, which introduces a very large source of uncertainty that could be as large as 0.4 dex, or a factor of 2.5, for individual black hole mass measurements. So for the rest of my talk, I'm going to show you how we can try to get around this problem by actually modeling reverberation mapping data directly to constrain what the structure of the broadline region is and hopefully obtain more precise measurements of the black hole mass. So in general, the way that we've gone about doing this is both trying to model the AGN continuum light curve and the distribution of sort of gas in the broadline region in order to construct simulated reverberation mapping data that can actually be directly compared to real data sets. And so if we work in a framework of Bayesian inference, we can actually infer things like the black hole mass while incorporating all these other sources of uncertainty in, for example, how the data is sort of measured. Okay, so just to summarize what we found so far, we've applied this technique to 16 different AGN now, and we found that we can measure the black hole mass more precisely than the traditional 0.4 dex limitation. In fact, we can measure it down to 0.1 dex. We've also been able to see what the geometry looks like, at least for the H-beta broad emission line region, which is sort of the most commonly measured. And so here I'm showing some examples of what that geometry looks like for 7 different AGN from the LIC AGN Monitoring Project 2011. And these results were done in collaboration with Peter Williams, who is a graduate student at UCLA. And so here is sort of an edge-on view of the broadline region, and here's a face-on view. And so you can see that these things are all thick disks viewed close to face-on. And there's some asymmetry in how you see the emission. It turns out that this emission would prefer to look back towards the central ionizing source, which is actually what photoionization models suggest. But we do see a range of dynamics that go everywhere from inflow, which is shown here in red, to outflow. But, you always wonder when you're applying such a simple model, how robust this is and how much you can actually trust these results. And so one of the things that I wanted to test was whether you took, if you took one AGN and you monitored it for 3 different reverberation mapping campaigns, would you actually get the same results out if you modeled them independently? And so that's what we've done for the AGN ARP151. It was monitored in 2008, 2011, and 2015. And here I'm showing you the AGN continuum light curves, the integrated H-beta light curves, and some individual H-beta spectra, because I think this is a good way to see the sort of range and data quality for these 3 different campaigns. All of them showed wonderful variability. All of them gave very nice constraints. So what do we get? Do we get the same results? So here I'm showing various parameters of our model. The top here is black hole mass, and here is just time. So 1 point for each of the different reverberation mapping campaigns. And if you look at the top, you can see that for the blue points, which are from our modeling, we do infer a consistent black hole mass for each of these different campaigns. And in general, the uncertainty on actually all 3 of the campaigns is smaller than the 0.4 dex uncertainty shown here by the red error bars on the black points that you would get from the standard approach. So that's very reassuring. And it turns out when we look at other parameters that shouldn't change, things like how thick the disk is, what its inclination angle is relative to us, its dynamics, those things also don't change. I should just point out that this time span is about 7 years, and 7 years corresponds to the orbital time at a radius of about 4 light days, which is sort of the mean radius that was measured for this first campaign. So this is a timescale in which something could happen. I mean, really, ideally, we'd like to look at this again in another 10 or 20 years and see what happens on longer timescales as well. But this does give us an avenue to at least look at the robustness of the modeling, or rather the reproducibility. The one thing that did change, though, over this short period of time was the size of the broadline region. So in 2008, the mean radius was about 4 light days. And then in 2011, it had grown to about 6.5. Okay, and it went up even a little bit more in 2011 or 2015. And this actually is not dependent on the type of modeling. If you just do cross-correlation analysis, which is sort of the standard reverberation mapping approach to getting a time lag, you see exactly the same thing. So that's these black points here. So even though the broadline region size is growing by almost a factor of 2 over these 7 years, we are able to consistently infer things like the black hole mass. So this was incredibly reassuring. The final thing I just wanted to mention is that the other comparison we can make is with other methods of trying to infer something about the broadline region. And this looks a little bit complicated, but really all this is a map of how much emission you get at which place across the emission line profile as a function of time delay. Okay, so this is sort of a map of all that information that's hidden in reverberation mapping data. And so traditionally, one of the ways that people had tried to infer things about broadline region structure was to generate this map. And so one of the best used tools for this is called MEMECHO. And so you can see it creates these beautiful smooth maps for these 3 data sets. But when we do our modeling, we get these much more sort of sharp maps here. However, it's really hard to compare them in these 2 spaces because each method sort of applies its own smoothing in a sense. And so what we did for these 3 data sets is we used our best fit models for each data set to generate simulated data that we then fed into MEMECHO. And that's what you get in this middle panel. And you can see that the middle panel and the right panel actually look very similar in terms of the sort of features that they have. And I think what this is demonstrating is that even with our simple model for the broadline region, we're still able to match sort of the overall features that are required in the data. Because, MEMECHO is not assuming anything about the geometry or dynamics of the broadline region. Unfortunately, we can't make a quantitative comparison yet because these maps also, these ones, do not have error bars. But when they do, then we'll be able to say things a little bit more strongly. So in conclusion, broadline region modeling has allowed us to learn some important things about reverberation mapped AGNs. It's given us more precise black hole mass measurements, and it's also told us what the geometry and dynamics are. specifically, looking at 3 different epochs of ARP-151 shows us that these results are at least robust to redoing them with future reverberation mapping campaigns, and that different methods are indeed consistent with one another. So finally, I just want to end with another invitation that all of you are welcome to join the last Equity and Inclusion Journal Club that is happening on Friday, May 18th, okay? And we're going to talk about, we're going to share what we've learned and look to the future of the CFA. So I really encourage all of you to attend, whether you've attended yet or not. I especially encourage people in positions of leadership here at the CFA to attend, and I hope to see many of you there. Thank you.
So ARP-151, the black hole mass, looked like it didn't change very much. It was a smaller variation than the red error bars. It looked like the 3 campaigns.
Yeah.
Does that suggest that the error bars for the single campaign black holes might be smaller than what we're currently estimating for the rest of the sample?
Sorry, are you talking about the black points?
Yeah, the black points look like to me that they're within, they're all within the red error bars quite comfortably. So that perhaps the red error bars were overestimated.
They may be. They may absolutely be. I mean, it's very hard to know what the uncertainty is. The uncertainty estimate of 0.4 dex comes from the scatter and the M sigma relation. So it may actually be smaller than that, yeah.
So the size of the accretion of the broad emission line changes and actually increases over 7 years. Right? Do also the average luminosity increase?
That's a great question. We looked into that, and it does not. And so for those of you who are not aware, there's this thing called the radius-luminosity relationship, in that the broadline region size is supposed to scale with the AGN luminosity. And this basically forms the basis of all of our large number of black hole mass measurements from a single epoch spectroscopy. What is not known currently is how the radius-luminosity relationship behaves for individual AGN instead of as a whole group. And so this is best studied by objects like NGC 5548, where we have like over 20 epochs. And I actually looked and compared it to NGC 5548, and there are at times at which NGC 5548 behaves similarly to this, which is that it will increase in radius without a huge increase in luminosity. There are also times when that object has behaved very strangely. So I think there's a lot of richness in looking at how radius and luminosity go together. And while I was a bit surprised to see no change in luminosity, it may just be that the picture is a little more complicated than we think about for the whole relation.
What physics does this F parameter that you mentioned at the beginning encode? What do you learn from your having measured that?
Oh, having measured just F?
Yeah.
Well, I would say that our main goal is to understand what the actual geometry and dynamics are, but the usefulness of backing out what F is that right now the average value of F that's used is just obtained from the M sigma relation, assuming that local black holes have the same M sigma relation as AGN. And this way we can actually test if that's true. There's also the added scatter of that relation having scatter. So this way, hopefully we can cut out some of that and have a more sort of less scattery mean value of F.
So a more technical question. At the beginning you mentioned that you use Gaussian processes to sort of interpolate your data. I'm wondering what kernel did you use and why? I always find it very difficult to choose the kernel, so I'm wondering what you guys did.
So we used it in the limit of basically a damped random walk for computational reasons of making it fast. So I think it's basically similar to what many people have used to model AGN variability. And I'd be happy to talk to you more in detail about that later. Okay.
Why are all 16 face on?
Well, because in the standard model of AGN, we expect to see edge-on objects have obscured broad emission lines, right? Those would be Seifert 2s. And so it actually makes sense that these would mostly be face-on, because that's when we can see the broad lines. So actually the fact that we find them all to be face-on is very encouraging. Yeah.
Physical model that helps you understand how the borderline region can expand so much in 7 years?
So that is a great question. Honestly, thinking about the way that the radius-luminosity relationship is usually described, my best guess for why this is happening is something about the way that the continuum variability is sort of interacting with the broadline region, because the shape of where the broadline gas is you're only going to see however much of it you're going to sort of probe with the variability features of the continuum. So if you have really like peaky continuum variability, then you might only probe the inner bit of the broadline region. And so those things, there are a number of people who've looked at sort of the theory of this and how you have to be very careful when you look at reverberation mapping data to sort of not conflate those two things. So I think it's just what we've observed, and unfortunately we don't really have observations between these three campaigns to help us figure that out.
Before we acknowledge Anna by thanking her, I'd like everyone to stay for 90 seconds afterwards. So, thank you very much. So this will be brief. I'm only here because Ali couldn't be here. And it's a little odd to acknowledge somebody with applause who's actually not physically present, but that's what we can do. So just like to us all to acknowledge the vision of this lunch that was Avi's. I thought he was crazy when he got started to allow 4 people to speak with PowerPoints, different laptops and one presentation. I think it's working very well. I think our conspirators today have shown how it can work exceptionally well. So let's just acknowledge 4 Annas and Avi.
Hi.
Can I ask you if you have also, because obviously when you say that it doesn't, it didn't change the luminosity,
Yeah.
you refer to the optical one.
I do. Yes. So that was another thing I didn't mention to you.
X-ray
We do not have it. We may have some X-ray data, but I haven't looked into